So let's see about aromatic compounds. In aromatic compounds, the main point what you need to learn is about EA's reactions only. That is
Yeah.
electrophilic, clear,
Yeah.
aromatic, substitution. Okay, this is the main reaction that you need to focus on. Basically, what we are expecting is when you have benzene or
Yeah.
any benzene type of aromatic compound, if you add an electrophile, it will get
Hmm.
substituted here. This is how it will get substituted. Clear?
Yeah.
Mechanism wise, if you notice, so electrophile will first get added up because direct substitution will not take place.
Hmm.
First, it will get added up here like this, getting a positive charge. Now, this positive charge can be migrated to uh, different positions, right? Because of the resonance stabilization which it can bring. So,
Hmm.
positive charge will be here like this, electrophile and H, which brings you the hybrid form of it. So, the hybrid form would look like this with electrophile and hydrogen here. Got it?
Yeah.
So, uh, this is the intermediate, and this intermediate is called as arenium complex here or sigma complex
Hmm.
or valent complex. It is also called as valent complex. Got it?
Yeah.
Second, right? See, so
Yeah.
this is the name of the complex here. Okay.
Hmm.
What is the important point we need to understand from here is that if you need to increase the stability, because the formation of this step itself is the rate determining step. This is the rate determining step. And what is the
Yeah.
second step here? That is, once you get an electrophile H double bond with plus charge here, you require a base to extract this proton so that aromaticity can be retained. Okay,
Hmm.
plus BH. So usually the first step is always the rate determining step, which means the stability of this complex drives the reaction more in the forward direction, or rate of the reaction will increase. Okay,
Yeah.
so how, because it is a positive charge, you can see that with respect to this electrophile at this position and this position, you are getting positive value here. So by chance, if there is any donating groups on it, it will always stabilize it. So remember that electron donating groups on benzene, okay, increases rate of EAS reactions. Got it?
Hmm.
Similarly, electron withdrawing group decreases rate of EAS reactions. Got it? That's why if you compare the rate in general with respect to any withdrawing or donating groups here, so by chance if you have methyl, it will definitely have more rate compared to benzene compared to NO2. NO2 is being a stronger withdrawing group. Understood? This is what
Yeah.
would happen. Okay. So usually it is always a two-step mechanism. This is how it will take place. Okay.
Yeah.
And electrophilic aromatic substitution can be reversible also, or it could be irreversible also.
Yeah.
Got it? Right. See, usually if electrophilic aromatic substitution is concerned, I can say there could be some irreversible reactions, or there could be reversible reactions. Okay.
Hmm.
Reversible reactions are usually observed when you have gases like SO3, CO2, and N2. Okay. So these
Hmm.
gases, when they start having high concentration, the reverse can always occur. Clear?
Yeah.
Second thing, reversibility. Acha, let me put it this way. Reversibility is based on either the reactant as in the products if you have gases, or the other case where reversibility is observed is when the electrophile is very stable.
Hmm.
If an electrophile itself is very stable, then also the reversible form can be taking place. So which means more than electrophile getting attached, the reaction can go more in the backward direction. Clear?
Yeah.
So for reversible cases, this is an important point you need to learn. For reversible, for reversible cases, correct? You will see uh, kinetic, kinetic, isotopic effect is observed.
Yeah.
Clear?
Yes.
So what does that mean? Suppose if you take rate of reaction, okay? So if you take our
Yeah.
rate of reaction for irreversible, you will see C6H6 will have same as C6D6 will have same as C6D6. But
Hmm.
rate of reaction for reversible cases will be C6H6 will be greater than C6D6 will be greater than C6D6. Got it?
Yes.
Clear?
Yeah.
So in these cases, you will see in the case of reversible cases, this is what happens, and in the irreversible cases, what would take place. Understood?
Yeah.
Next, orientations on EAS. Orientations via EAS reactions. Okay.
Yeah.
Orientation as in on benzene ring, if you have any group G, correct? This
Yes.
group G, when an electrophile is being added, it can make two types of substitutions in general. Okay.
Hmm.
So if it makes a substitution at this position plus this position,
Hmm.
like this here, then we call G is OP directing group. That means it is pushing onto ortho and para. This is ortho, this is para.
Yeah.
Correct? But if this group is giving a product like this, G with electrophile here, we call it as meta directing group.
Hmm.
Clear? So G is meta directing group. So this is another important term that you need to understand. Clear?
Yeah.
So here we can divide it into multiple cases. So I'll start with case 1. If group is O minus, NH minus, OH, NHR, NR2, NH2, okay, these
Yeah.
are very strong activating groups. These are called as strong activating groups. So basically, they will increase the electron density. Electron
Hmm.
density increases on benzene ring. Okay,
Yeah.
these are very strong activating groups here. Understood?
Hmm.
So whenever you see these groups, you should understand that we are talking about very strong activating groups. Okay.
Yes.
Next, case two, right? Case two is group which are OCH3, clear, NH, C double bond O CH3, these kind of cases. O C double bond O CH3, correct? So they are still connected, but yet these are not completely as strong as the first one. So it is moderately activating group.
Hmm.
They're moderately activating groups. Okay,
Yeah.
इसमें भी electron density बढ़ता है. So
Yes.
electron density on the benzene ring increases. Okay, case 3 group could be as simple of CH3, C2H5, CH and this one, and CCH thrice. Okay, tertibutyl.
Hmm.
So this is the order also in which it will activate or deactivate. Okay, so this would be
Yes.
weakly activating, weakly activating groups.
Hmm.
Clear? Here also electron density increases. Correct? So that
Yes.
means all of these groups will have more electron density than only benzene. Correct?
Okay.
Clear?
Yeah.
Okay. Next, case 4. Case 4 is the group which will be mildly withdrawing. Like you have CH2Cl, CHCl2, got it?
Hmm.
Chlorine, bromine, iodine, NO, okay? Uh,
Yeah.
Fluorine also, got it? So these are the cases by which they are withdrawing. Clear?
Yes.
Now these are weakly, weakly deactivating, weakly deactivating. Okay. Another
Yeah.
thing I can write is if you have CH2 like this also, C triple bond CH also, and CH double bond CH with electron withdrawing group, or CH double bond CH with electron, sorry, only electron withdrawing group like this. Okay. So these are all the cases which are weakly deactivating. Understood? Next, case 5 or groups, and here electron density decreases.
Hmm.
Yeah. And lastly, if you have groups like aldehyde, ketone, okay, esters, amides,
Hmm.
and anhydrides like this, okay, these are moderately deactivating,
Hmm.
moderately deactivating. Here also electron density decreases. And case 6, G will be NO2, Nr3 plus, okay, uh,
Yeah.
cyanide, SO3H, COOH. Got it? These are strongly, these are strongly deactivating,
Yeah. Okay.
the strongly deactivating groups. So you can see electron density decreases in this case. Okay.
Yeah.
So these are the cases we need to check out. In which case it is increasing or in which case it is decreasing. Clear?
Yeah. Okay.
Okay. General tendency, what it is? Okay. General general rate of reaction, if you compare as a group wise, if you compare, this is how you should compare: OH, NH2, NR2. These kind of cases will be greater than OC double bond O CH3,
Hmm.
NHC double bond O CH3. These type of cases
Hmm.
compared to CH3, C2H5. These type of cases compared to
Yeah.
fluorine, chlorine, bromine, iodine, NO. These kind of cases, and
Hmm.
compared to aldehyde, okay, ketone, ester, acid chloride, these type of cases. Then comes acids, okay, sulfonic
Yeah.
acids, cyanides, nitro groups. Okay, this is the general order. Okay, beta. So if
Yeah.
you notice this order, you should be able to figure out whether the electron density is increasing or decreasing. Okay.
Okay.
So from here, what is the conclusion? See, case 1, 2, 3 or electro uh, groups are 1, 2, 3. Groups are activating. Okay, activating groups. Got it?
Hmm.
And case 4, 5, 6 are deactivating groups. Clear? And
Yeah.
this is for one important point. Second important point is case 1, 2, 3, 4 are OP directing groups.
Mm. Yes, sir.
Got it? And only case 5 and 6 are meta directing groups.
Mm.
So although it appears like 1, 2, 3, 4, if you notice 1, 2, 3, 4, correct?
Yeah.
In 4 it is deactivating. Yet even though it is deactivating, it will be good for OP directing only. Okay. So
Yeah.
remember this fourth one is an exception. Okay. Although it is deactivating, it will still be OP directing. Okay.
Mm. Yes, sir.
Any doubt here?
Understood.
Okay. Lastly, another important point, when suppose if you have multiple groups here, okay, so in multiple groups, what is the point you need to learn? Okay, if two groups two groups are present, two groups are present, and in that group 1 is activating, and group 2 is deactivating, then priority is for group 1, uh, activating
Mm.
group 1 for EAS reactions. Okay, so you need to follow as per group 1. Clear?
Okay.
Next, if group 1 is deactivating, clear, and group
Mm.
2 is also deactivating, if both of them are deactivating, understood?
Yeah. Yes.
Then priority is based on most deactivating. Okay. Or
Mm.
similarly, if you have both activating, most activating, so you need to check out for most activating case. Clear?
Yeah.
Make sense?
Yes.
Now let's see what are the types of reactions we will come across. Okay, in
Yes.
EAS we will come across first nitration. Okay,
Mm.
for nitration, the reagent that we use, this is called nitrating mixture.
Mm.
Nitrating mixture, that is the mixture which produce NO2. Okay, so
Mm.
that include first one, HNO3 plus concentrated H2SO4. This is one. Or dilute or concentrated HNO3 directly can be used, or we can use NO2BF4, basically NO2 plus and BF4 minus, or we can use NO2 plus and ClO4 minus salts. These kind of compounds will give you nitrating agent, used
Mm.
as a nitrating agent. Out of this, the most used and what is given in NCERT is the first one. Okay,
Mm.
and this is something you should remember, that if you have H2SO4 plus HNO3, the reaction that happens is HSO4 minus plus uh, you know NO2 plus H2O. Got it? So
Yeah.
this is nitronium, known as, the electrophile is known as nitronium ion. Okay, so nitronium ion is created, and based on nitronium ion you should know what is the product we can get. Okay, for
Mm.
example, if I take uh, let's say I react this NO2 plus is been treated with various reagent starting with benzene.
Yeah.
If you take it with benzene, you will get it as nitrobenzene. Correct?
Yes.
Similarly, if you take it with toluene, correct? With toluene,
Mm.
you will get, you know, nitro at ortho position and nitro at para position. Okay. Generally, you will notice that para is major, but in this case, ortho is major.
Yeah.
Major and minor. This is an exception. Clear?
Yes.
Otherwise, most of the time it is the para being major. Correct? Hmm.
Yeah.
Next, if you have chlorobenzene,
Yeah.
we just learned that in the case of chlorobenzene, what would happen, beta? Uh, ortho and para only is favorable. Correct?
Hmm.
So ortho and para is favorable, and in this case there is no exception. Para is major. Clear?
Yeah.
Likewise, if you take something like benzaldehyde, got it?
Yeah.
Benzaldehyde. So here also it is meta directing. So if you have an aldehyde here, so nitro will come at this position. Got it?
Yeah.
And if you have uh, acid also, you will have this as COOH with NO2. Correct? At this
Hmm.
position only you will have. Okay. And lastly, if you have OME also, OME, OME will favor ortho and para. Okay.
Yeah.
So you will have OME with nitro and OME with para, and which is major? Para is major. Got it?
Hmm.
So you got a gist of it, how the
Yes.
nitration happens, beta. Okay.
Yeah.
So this is how the nitration takes place. Okay.
Hmm.
Now, what is the exception in the case of nitrogen that usually happens is with aniline. This is again an exception, important exception. In the case of aniline, when you are using
Hmm.
concentrated HNO3, clear, in the presence of concentrated H2SO4. Now, problem what happens here is, okay, although it is supposed to be ortho and para directing, correct? So this is what you
Yeah.
should get. Ortho and para we should get. The problem what happens is here it is only observed 2%. This is observed 51%. But at the same time, meta is also observed.
Yeah.
Meta will be observed, which is around 47 percentage. Clear? Now this exception, why this has been an exception is because in the aniline is actually basic in nature, and you are putting in an acidic medium that
Yeah.
leaves you with anilinium ion NH3 plus. Got it? And
Yeah.
NH3 plus is a meta directing group. Got
Yeah.
it? So there will be sufficient amount of anilinium ion formed, because of which we will also get, NO2 present here, and thereafter H plus can be removed out and you can get this product. Okay. So this is the exception with aniline. Okay.
Yeah.
Now similarly, another important part of exception is with phenols. Okay. Phenols, when you do dilute HNO3, when you react with dilute HNO3, you don't have much problem here. You will get ortho and para. Correct.
Yeah.
So OH here and NO2 here. Correct. But the problem comes when you have concentrated. Okay, don't play with. Problem comes when you have concentrated form.
Yeah.
Clear?
Yes, sir.
So if you have concentrated here, concentrated this one with concentrated H2SO4. Now,
Yeah.
along with this orthopara, you would actually get an oxidized product, which is quinone. Okay,
Yes.
clear? And this will be major.
Yeah.
Understood. So that's why with concentrated HNO3, you cannot get this. Okay. In fact, not just that, more than getting these products, these will be minor. Correct. This would be minor. But the major product would be either quinone, or there will be the next major product. I mean, the next significant product will be this one, which is picric acid.
Yeah.
Got it? So somehow we need to avoid this in case if you want to make a nitration, concentrated HNO3. Okay. That is what we'll learn in phenols. Understood? Clear?
Yes.
So this will be low yield for now. Main yield will be quinone. But to increase this quantity, we can add some sulfonation is been done, and thereafter it is been enhanced. For example, like this. If you have phenol, correct, you first only add concentrated HNO3, sorry,
Yeah.
H2SO4. When you add only concentrated H2SO4, it will give you sulfonation like this with SO3H. Correct. And now when you do concentrated, in fact, uh, when you are doing this sulfonation, it can, if you take excess also, you will get at two positions only. You will not get at three positions. Thereafter, when you now divide, react that with concentrated HNO3, now desulfonation will take place. Along with that, NO2 will come onto the picture, and that's how you'll get picric acid as major product.
Yeah.
Okay, so this is a very important and very significant role that plays by sulfonation. I
Yes.
guess this point is clear as well. Yeah,
Yeah.
how the sulfonation takes place here. Got it. Right. And second thing, another question that is familiarly asked here. So let me call this as compound 1 and compound 2. Okay. Between these two compounds, there could be something which has been asked. One is acidic strength. Okay. Acidic
Yeah.
strength, naturally, we expect ortho should have more. Here, due to the hydrogen bonding between OH and NO2, para is more. So 2 is greater than 1. Okay. This is first exception. Second thing, when it comes to boiling point, and because of the intra-edge bonding, the boiling point will also be lesser. So para will have more boiling point than the ortho. Okay.
Yeah.
And listen, whenever there is a hydrogen bonding at ortho position, because of which there is a large boiling point difference that has established, then we can separate these two. Okay. We can separate these two products. Separation method. The separation method which is used to separate these two is called steam distillation.
Hmm.
Steam distillation. Okay. Right.
Yeah.
These are all the important JE points, beta. Got it?
Okay.
So how the aniline reaction happens, phenol happens, right? What is the exception in phenol? What is its acidic strength, boiling point, steam volatility? Everything is being asked as a question here. Clear?
Okay. Yeah.
So I guess this part is understood. Right. Next. Now let us focus on sulfonation. Okay. The second reaction is about sulfonation. Okay.
Hmm.
Only sulfonation. So now the reagent that we use here is simply either concentrated H2SO4 or oleum. Okay,
Hmm.
oleum is a mix of H2SO4 and excess amount of SO3. Correct. This
Yeah.
is the one. And now, how does the reaction take place here? Check it out. If you have, uh, sorry, in concentrated H2SO4, if you notice the mechanism, it has been said that one H2SO4 will act like a base, the other H2SO4 will act like an acid. Okay,
Yes.
and that would give us HSO4 minus plus H2O plus HSO3 plus. Got it? Now this
Yes.
HSO4 minus plus HSO3 plus can further react with each other to convert into again H2SO4 plus SO3. Got it? So that
Yeah.
means this can further give away, I mean, where you have HSO3 here, this H plus will go away, OH will come out of it and it will become SO3. Got it?
Yeah.
Okay. Now, what exactly we are getting is SO3. Here, there is one important aspect to understand. Either you write it as HSO4, HSO3 plus or SO3. Both are both are used as electrophiles.
Yeah.
Okay, clear
Yes.
beta? Mostly in JEE mains, SO3 is more focused, correct? But if it
Yeah.
is in advanced, it has been already asked. Both HSO3 plus as well as SO3, both of them are electrophiles. Okay, both will make the reaction. Got it?
Hmm.
Now, just like above, if you make the reactions here, let me just copy this part because this is the same thing we are doing again. Okay, if you do the same thing for sulfonation now, got it?
Yeah.
Now, like I said, I can take both HSO3 plus or SO3. I'll stick to SO3. Okay,
Yeah.
so if it is SO3, if you react with benzene, it will become sulfonic acid, benzene sulfonic acid, SO3H. If you react with toluene, right, it will become
Yeah.
ortho product as well as para product. Done.
Yeah.
And if you react with uh, where is it? Yeah, chloro here, same logic. With chlorine also, we can have sulfonation done, SO3H and SO3H. Got it?
Yeah.
And with this also we can have anisole also we can have SO3H and SO3H. Clear? Now this
Yes.
exception is not valid here. Correct?
Yeah.
The major now will be only this one.
Okay.
Para is only major in this case. Okay.
Yeah.
Same way here, if you have it para position, you will again get this as SO3H, and here
Yes.
also you will get this as SO3H. Got it?
Yes.
Usually, how the benzoic acid is reacting is never asked, but nitro, how it is acting, nitro group, how it is acting, that will be asked. So that's why I'll change this part as NO2. Okay. So this is what you need.
Yeah.
Again, here, what is the exception is, how the aniline reacts. Okay. So when it comes to aniline here, correct. And when aniline reacts with concentrated H2SO4 here, okay,
Yeah.
first it will become an acid base reaction, which means you will have NH3 plus and HSO4 minus. This is an acid base reaction. That's why this reaction is always facilitated with some heat. So as soon as you heat it again, you will get this as NH3 plus here, and here you will get SO3 minus. Correct? And
Yes.
this will exist like a Zwitter ion. Okay? A dipole ion. Zwitter ion is also called as a dipole ion. Clear beta?
Yes.
Right.
Yeah.
Next. Now, the important reactions of sulfonic acid here, SO3H, there are two important things. One, if you react with fused NaOH and heat, basically fused itself is a heat form, then first you will get this as O minus Na plus, and then later on hydrolysis will give you phenols. Very, very important reaction this is. A lot of time we'll
Yes.
forget what happens in here. Okay, it is very important. Next one, if you notice that SO3H, and you react this with H plus, dilute H plus, okay, not concentrated, dilute H plus and heat, correct?
Yeah.
This will give you complete desulfonation and you'll get a hydrogen here. Got it?
Yeah.
Any doubt here?
Yes, sir. Was understood.
Right. Now, these two reactions are also called as ipso substitution. Ipso substitution. That means at the same functional position, we have a substitution done. Or because you are doing removing a sulfonation, also known as desulfonation reaction. Okay.
Hmm.
Is this part clear, beta?
Yes, sir.
Right. So as much as the sulfonation is concerned, these are the points we need to remember. Okay. Next, third one
Yeah.
is about halogenation.
Yeah. Okay.
Third one is about halogenation. Now, usually how the halogenation works here is X2, you take it mostly in the liquid form. Maybe you take some support of ethers or something, convert that into liquid form, then react that with AlCl3, dry, okay? So just add some AlCl3 here. Instead of AlCl3, we can always take directly iron. We can take FeX3. We can take any form of AlX3, or we can take BF3. What are all these? These are all Lewis acids.
Hmm.
These are all Lewis acids. So in the presence of Lewis acid, what can you expect is that X plus can be formed here, and that is an electrophile. So wherever you see this case, right, that means we are trying to generate an electrophile. Now the interesting and important part here is rate of reaction. Okay, rate of reaction, which is EA's reaction. If you take respective halogens, fluorine will have more reactivity, then chlorine, then bromine, then iodine. Okay, this is
Hmm.
unlike the SN2 reactions where iodine has more reactivity. Here, fluorine will have more reactivity. Okay,
Yes. Okay.
the point is clear, beta.
Hmm.
Right. So, therefore, if at all I take up the same thing here, what we had done, and you try to make a halogenation
Hmm.
of all the groups here, check out. If you have X plus here, and now you're reacting with all of these. Okay.
Yeah.
Then first with benzene you will get halobenzene. Okay. With toluene you will get uh, ortho and para. Okay. So
Yes.
and again para is sorry in this case also same exception is valid. Let me rewrite that. Yeah. Here also the same exception is valid. Here chlorine and chlorine will be present. Let's say specifically it is given for chlorine. I don't have information on bromine and iodine, but you can always take it as a generalized form. Okay? So
Okay.
major for chlorine is only something which you need to remember thoroughly. Okay. So for
Yeah.
chlorine, you will see major is ortho and minor is para. Okay.
Yeah.
Hmm. For other cases, it is always the reverse beta. For bromine, fluorine, and iodine, para is only major in the unlike in chlorine case. Okay. Hmm. Next. If you have chlorine itself, you can get dichloro group. So there is no
Yeah.
problem here. So chlorine and chlorine, this is major. Okay. So here if you have OMe, same logic here also we can get chlorine and chlorine, and this is major. And here also if you have para position, I can get chlorine. Here also para position, I can get chlorine. Done. So these are typical reactions of halogens beta. Okay. Now let's see what are the important exception reactions here. Clear? Exception reactions, what you need to note is about phenol and aniline. So when it comes to phenol, let's say when the chlorine or bromine is being reacted, especially the reactions are more concentrated for bromine.
Hmm.
So if at all I take bromine in CS2, okay, because you will not have sufficient availability of Br plus because you are using a non-polar solvent, you will get Br here. The reason is non-polar solvent. It will fall. Non-polar solvent.
Hmm.
Okay. Otherwise, if we take Br2 in the presence of H2O, got it? Br2 in the presence of H2O, that is bromine water. Okay.
Hmm.
In the presence of bromine water, now the addition would happen at all three positions. Got it? I'll get this as
Hmm.
OH, Br, Br, and Br. And this is a white PPT. Got it? This is some important points you need to understand that it is a white PPT. Clear?
Yes.
And this is used to detect the presence of phenol. Got it?
Hmm.
This is an important exception. Okay. Now what happens with aniline here is, okay, with aniline, what is expected out of you is that when it comes to aniline, whether you take both of these, I mean, whether you take bromine in CS2 polar or non-polar, in both the cases, aniline being such a strongly activating group, it would give you bromination at all three positions, and this is also a white PPT. Okay, clear? And of course, this is not detected for aniline, but yeah, this is a white PPT. Got it? Clear on this point? Right. Now, what is being usually asked in this case is that how, okay, see this example, how aniline can be only brought with one Br. Instead of two Brs, I require one Br. So most of the time in anilinium reactions, you will do acetylation in the presence of pyridine maybe. Then in the presence of acetyl group, you will get this as NHC double bond OCH3. Okay.
Yeah.
And now when you do bromination, right? Now when you do bromination in the presence of maybe acid like this, so then you will see only one Br will come because it is a moderately activating group. And it is bulky enough, so only para will come as major, although will hardly be observed. Okay. And once you get this product here, now you do NaOH and heat here. So that acidic group will go away and you'll bring back NH2 Br plus CH3CO minus Na plus. Understood? So what we are getting? We are getting only one substituted bromine. So this is another very common thing that is being asked. Clear, beta?
Yes, sir.
Now the next common thing that is being asked is this one. The question wise I'm saying, question wise, another thing that is being asked is, if imagine I already have OH with SO3H here, or let's say OH with COOH here, correct? Understood? Or you can have multiple substitutions also. Okay, one second, just a minute. Right, see beta.
Yeah.
By chance, if you have these groups, even if you have a groups, multiple number of groups like this, SO3H and COH, all of them, correct, when you are reacting with bromine water, they all will get replaced. Okay, ipso substitution will take place and everything will be replaced and you will get only bromines at all three positions eventually. Got it? Now this is something that you need to understand. Okay? So these are the important reactions of halogen forms. Correct?
Yeah.
Now the fourth reaction is about alkylation. Okay? The fourth one is about alkylation.
Yes, sir.
Okay. Alkylation reactions happening this way, where you have alkyl halide reacting with AlX3. Correct? In the presence of AlX3, first you will get this as almost R plus and AlX4 minus. Now that might be a complete carbocation, okay, or it might be without a carbocation having a high positive charge. Both can happen, okay, clear? Now what all things we need to check here? Suppose if you have a primary position like this, okay, right? So if there is an alkyl halide here like this, okay, clear?
Yes.
If you take AlCl3 at low temperature, correct, no carbocation,
Yeah.
right, then you do not make any carbocation. Clear? So
Yes.
even if you have secondary also like this, correct, with AlCl3 low temperature, no carbocation, no carbocation, correct?
Yeah.
Okay. Even if you have like this, okay, like this with AlCl3 low temperature, no carbocation. So you directly make a reaction there, correct? But if you have like this with normal temperatures, okay, so in all these cases, let me just copy it directly.
Uh,
In all these cases, if you have, okay,
hmm.
normal temperature, normal
Yeah.
temperature and normal temperature, then you will see carbocation is forming in all the cases. Okay,
Yes.
this is with AlCl3. Okay, other Lewis acids
Yeah.
are weak. Other Lewis acids, okay, like FeCl3, BF3, SnCl2, ZnCl2 are weak. So no carbocation in any case. Correct?
Okay.
So
Yes.
that's the point you need to remember while making alkylation as well. Okay.
Hmm.
Hmm. Right.
Yes, sir.
So usually if you have alkyl halide, this is how alkylation is being done. Okay. Now,
Yeah.
what if you have an alcohol or an alkene? Okay. So
Yeah.
this is like case one. Okay. So if you notice case two here, suppose if you have an alcohol, okay, for alcohol, we can again use Lewis acids or, you know, concentrated H plus, which can come from concentrated H2SO4 or concentrated H3PO4. Correct?
Hmm.
And
Yeah.
usually Lewis acid which are used are BF3 is most used, frequent. This is
Yes.
frequently used. Okay. Now this will create carbocations. In all the cases, carbocation is prepared.
Yeah.
So in all these cases, carbocation is being made. Okay, beta? Hmm.
Yes.
Same way, if you have an alkene, right?
Hmm.
Alkene like this, clear? And for that, we require, you know, concentrated H plus. Again, that comes from H2SO4 or concentrated H3PO4. Understood?
Yes.
That will create a carbocation following Markovnikov's rule.
Hmm.
Following Markov rule. Understood?
Yes.
Right. So this is the case in which you will see again this kind of reaction could take place. Okay. Now another place where this reaction can happen, I mean alkenes can happen, is you can take HF at 0 degrees centigrade or PPA, polyphosphoric acid at 0 degrees Celsius. They will also give you the same thing. Got it?
Yeah.
Understood? Right.
Yes.
So these are the places where you can actually prepare carbocations and hence make an ES reaction. Clear?
Huh.
Right. So now what are the types of reactions that you will get? Directly we'll get into the reactions. Correct? So
Yeah.
these reactions, beta, where you are making an alkyl substitution, okay, using an Lewis acid. Alkyl substitution, alkyl substitution
Hmm.
using Lewis acid is called as Friedel-Crafts. Friedel-Crafts alkylation. Understood now?
Yeah.
This is Friedel-Crafts
Yes.
alkylation. So now quickly, if you go through certain questions here, check out these are most asked questions. So if you have benzene and sorry, if you have benzene plus this chloride here in the presence of AlCl3, most of the time if temperature is not mentioned, you will take it as normal temperature. That
Hmm.
means you'll make a carbocation rearrangement and then this will be the major product. Then
Hmm.
any doubt there?
Understood.
Similarly, if you have benzene plus CH2Cl2. So if you have CH2Cl2, that means you have to take it as 2:1 ratio. In that case, alkylation in the presence of AlCl3 happens two times
Yes.
and you will get two phenyls connected this way. Got it?
Hmm.
Next,
Yeah.
next, if you have benzene at which it is already some connection of alcohol is present, let's say like this. Okay,
Hmm.
clear?
Yes, sir.
In that case, if you react with concentrated H plus, so you will see the internally EAS will take place like this. Okay, this is the internal
Yeah.
EAS that will take place. Okay, just a second. So now check it out. If you notice the next one, uh, I have a phenyl group here, correct? I mean benzene,
Hmm.
and then we have benzyl chloride here, like this. Benzyl chloride with AlCl3. Again, you can get the same thing like this because a carbocation can form here. You can get that same product. Clear?
Hmm.
Similarly, if you have benzene, right, and I'm treating that with alkene here, correct, in
Yeah.
the presence of HF at 0 degrees. So you will get tert butyl here like this, correct? And benzene,
Yeah.
if you have alkyl halide here with AlCl3, again you will make it as tert butyl. But
Hmm.
if you have Cl with SnCl2 or FeCl3, then you will not make any rearrangement, correct? And this is the product you will make it. Understood?
Yeah.
Right. So these are the type of reactions, Friedel-Crafts reactions that you should be aware of. Understood? Other than that, few more Friedel-Crafts reactions include something like this. Benzene. If you have, you know, group like this, and then you're treating with BF3 first, BF3 will get connected onto the lone pair of oxygen, and thereafter this is the position where the benzene will attack. So you will have like this with O minus and I mean not O minus, O with BF3 minus, and
Yeah.
internally this will take away H plus from here, and that's how it will retain the aromaticity. So final product will be
Yeah.
like this, OH, and this is the final product. Done?
Hmm. Yeah.
Here, beta. So these are
Yes.
few worked out cases you need to understand how that
Yeah.
reaction takes place. Okay.
Yes. Hmm.
So in the case of alkylation, this is what you need to know. Okay. Next, when it comes to uh, chlorobenzene, let's say I already have chlorobenzene here, correct?
Yeah.
Then what type of ES does that take place? Here, if you notice CH3Cl in the presence of AlCl3, you will
Yeah.
definitely get chlorine, one methyl here at ortho position, and one methyl at para position. Okay, and this being major. Clear?
Hmm.
This is how it will happen. Now, the important point about Friedel-Crafts reaction is that if you take excess, let's say CH3 is there, and again I'll make CH3Cl. Suppose if this is excess, so you will get lot of poly substituted products. So which means you can get this one, you can get this one, you can get like this. Poly substitution can take place. Got it? These kind of products can happen. So poly substitution is possible in all of these cases. Okay,
Yeah.
poly substitution will take place. Correct?
Yes.
Okay. And apart of it, when it comes to chlorine, what is the important reaction that you need to remember as a ES reaction is that chlorine, when you react that with CCl3, C double bond O H, got it? If you react with this one, this is called
Hmm.
chloral. Okay, in the
Yeah.
presence of chloral, so what do we get here is that we will get this chlorine adding on the para position here. Okay.
Mm.
With this part, this has to be done in acidic medium. Sorry, I did forgot to make that acidic medium. So if it is acidic medium, this lone pair is the one which will take H plus, creates a delta positive on carbon. From para position, it will push. Okay. So this will have OH, and here you will have CCl3. Yeah. This is the first product you will have. And if I take second mole here, again, if at all I take H plus and I take chlorobenzene again, so two times that substitution will take place, and you will get like
Mm.
this one with CCl3. Correct?
Mm.
This is what you will get. Okay, with two chlorine groups here. And what is this called? This is called DDT. Okay, dichloro, dichloro, diphenyl. Okay, trichloro,
Mm.
trichloroethane. Understood? This is the
Yes.
structure of DDT. So as much as ES is concerned, ES reactions are concerned, these are some things we should be aware of. Okay.
Mm.
Now, just like Friedel-Crafts alkylation, we can also have acylation. If you notice
Mm.
acylation reactions, okay, here we'll
Yes.
take RC double bond of X that is been treated with ALS X3, and here complete carbocation is formed in all the cases. Because this carbocation get resonance stabilized easily as RC triple bond O, and this is called as acylium carbocation. Got it? So because of the
Mm.
acylium carbocation formation, this makes more easy to uh, come out as carbocation here. Okay, and in which cases we can make acyl group here? See, one is RC double bond O Cl plus AlX3. This will create RC double bond O plus. Second case, you can have RC double bond O, C double bond O, OR, which means it is an anhydride. In the case of anhydride also, you will see this as C double bond O plus and RCO minus AlX3. I mean minus and plus here, okay? This is the one which you will get, okay?
Yes.
And next, if you have even acids also, RC double bond O OH with
Mm.
you know concentrated H plus. H plus can come from H2SO4. That can also give you plus H2O. Then these are major ways by which you can get the acylation done. Okay. Typical acylation, we can notice it from these examples. You can see how the examples are being asked here when it comes to acylation. So let's say I have a compound like this, OET, okay, and this is being treated with, correct, concentrated H2SO4 first. Sorry, dilute H2SO4 first. So esters will first undergo hydrolysis. Understood?
Yeah.
So we will get this as OH. Got it? And thereafter, suppose this is the second step. Basically, this and ethanol both will form. And this, if you react with concentrated H3PO4, let's say. Now, this will also give you acylation. So here we can get a double bond O with positive charge where benzene will attack, and that eventually become a six-membered ring like this.
Yeah.
Correct. This is the acyl product which you will get. Okay.
Yes.
Any
Yes.
doubt here?
No, sir. Understood.
Another question which is always been asked here is, suppose if you have already existing some group, some OCH3 group here, okay, clear. And then on this meta position, I have 1, 2, 3, 4, okay, 1, 2, 3, 4 here. And on fourth position, I have acid chloride here. And this compound is been treated with AlCl3. Got it? Now
Yeah.
you might be usually confused, should I put it at ortho or should I put it at para? So usually
Hmm.
major product will always be at para. Okay.
Yeah.
So what you should do, if you have this as OCH3 here, from this position, six-membered ring is formed. This is major. Correct.
Yeah.
This is something which we need to understand. Okay.
Hmm.
So acylation could happen this way. Okay. Most of the
Yes.
time, most of the time, whenever you do acylation is always carried out, you know, by carried out by Clemenson's or Wolff-Kishner reduction. Okay. If you have zinc and mercury amalgam in concentrated HCl, this is called Clemenson's reduction. And in the presence of Clemenson's reduction here, I mean, in the reagent, in the presence of this reagent, the keto group will get reduced beta. Okay.
Hmm.
And usually, whenever you have a cyclic structure, selenium and heat or sulfur and heat will convert that into aromatic ring.
Hmm.
Got it? So, this is a very standardized question that starting from acylation, you are going all the way towards naphthalene type of rings.
Yeah.
Any doubt here?
Hmm. No, sir.
Clear, right? So,
Yes.
now one thing you need to understand about Friedel-Crafts reaction. Okay,
Yes, sir.
Friedel-Crafts reactions is that it is valid for valid for okay moderate 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 activating groups, moderate activating groups, weak
Yeah.
activating and deactivating groups, deactivating groups beta. Okay,
Yes, sir.
let me list out here group wise. If you notice, OCH3,
Ah.
CH3, C2H5,
Yes.
okay, CH2Cl, CHCl2, fluorine, chlorine, bromine, iodine, NO, okay,
Yes.
NH, C double bond O CH3, O C double bond O CH3, CH double bond CH2, C triple bond CH, okay.
Yes.
When you see these groups, these are the only cases where Friedel-Crafts is valid, okay.
Hmm.
Friedel-Crafts does not give any great reactions with either strongly activating or strongly deactivating or moderately deactivating, okay.
Yes.
So that's why you see that, okay, OH, OH, COOH, CHO, if at all you react with CH3Cl in the presence of AlCl3, here the reaction will take place and you will get poor yields, okay. But
Yeah.
if you take NH2, NR2, NO2, correct, these
Yes.
are very strongly donating or strongly withdrawing, correct.
Yes.
So in that case, there is no reaction. That's it. These are the Friedel-Crafts cases you need to know. In which case, what happens? Okay,
Yes.
right. Last of the reaction here is about free radical reactions.
Yeah.
Okay. So usually we can have two types of free radicals. One is directly X2 in the presence of H nu to give X dot. So here you will have rich amount of
Hmm.
rich amount of source. Okay. But if you have double bond O, N, and Br here like this. This is known as NBS, N-bromosuccinamide. Okay.
Yeah.
Here the Br dot is, okay, low concentrated. Got it?
Yes.
When you have low concentrated, usually we will get only one addition.
Yeah. Yes.
Example, if you take benzene, you react with this Cl dot, I mean Cl2H nu. Cl2H nu, only one equivalent. We are taking low concentration. What do we get?
Hmm.
Alkylate chlorobenzene. Hmm?
Yes.
If I take Cl2, okay, H nu in the present and excess, correct? In that case, you will see addition reaction more than substitution.
Yeah.
Excess halogens will always give you addition reaction. Okay,
Yes.
this addition reaction product is called gamaxene.
Hmm.
Okay,
Yes,
similarly, if
sir.
you take benzene and you react with Cl2, okay, with one equivalent with AlCl3 or dark, sometimes it is mentioned as dark, so only one chlorine. Hmm?
Yes.
If you take Cl2, AlCl3 with excess amount,
Hmm.
in that case you will get this as Cl, 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 and Cl. So what is the product here? C6Cl6. There is no hydrogen here.
Yeah. Okay.
Cl6. Okay.
Yes.
This is called as HCB, hexachlorobenzene. Okay.
Yes, sir.
Well, here this is C6H6Cl6, known as, BHC, benzene hexachloride. So there is a difference in understanding of these two terms. Okay. Just be careful
Yeah.
with it. Clear, beta? Right.
Yes.
Next one. If there is methyl, I mean, if there is a toluene and then you are reacting with Cl2 and H nu, always notice that first equivalent will go towards this position only, one equivalent. Okay.
Yeah.
And if you are treating that with uh, excess, Cl2 excess, now this time don't do it on benzene. Okay.
Hmm.
Only do it on toluene position, CCl3. This is what is expected out of you. And this on hydrolysis will make it into an acid, benzoic acid. This is the
Hmm.
sequence again very commonly asked. Got it?
Okay. Yes, sir.
This is about the free radical reactions. Got it?
Yes.
Lastly, when it comes to oxidation,
Hmm.
benzene directly, if you treat with V2O5 at around 300 degrees Celsius, we shall be able to oxidize this to phenols. But if the same V2O5 is been treated at around 500 degrees Celsius, it will convert into an anhydrate like this. This is called, maleic anhydrate, coming from maleic acid. Okay.
Yeah.
And next, in case if you have toluene, correct, like this, and react this with KMNO4. Okay.
Yes.
Whether you take acidic medium or basic medium, right? Usually you will end up getting this as an acid, COOH. Got it? In
Hmm.
fact, if you take KMNO4 in H plus or K2Cr2O7 in H plus or
Hmm.
concentrated HNO3, correct? These
Yeah.
three are good reagents for making oxidation reactions. Okay. So
Yes.
in case if you react with benzene like this, okay,
Yes.
now you notice that there should be one alpha hydrogen. That is a criteria. If you have one alpha hydrogen, it will convert into benzoic acid. This is known as side chain oxidation. And the rest of
Hmm.
the two carbons will also convert into an acid form. Okay.
Yeah.
Second, if you have like this, then here also it will become COOH. plus 2 moles of CO2. Okay, single carbons will convert into carbon dioxide. Okay,
Yeah.
if you already have a double bond also, that will even help it better to make it into convert
Hmm.
that into carboxylic acid.
Yes.
Next,
Okay, sir.
if you have tert butyl, no reaction. If you have tert butyl, then there is no reaction. Okay,
Hmm.
and in case if you have groups like this, then the second ring will get oxidized on both the sides, and the other one being oxalic acid. Oxalic acid can be further oxidized, but just go with the options what is given. Okay,
Yeah.
whether the options have that or not. Okay.
Yes.
Next, if two rings are given, out of which one ring is donating like this, then
Hmm.
always oxidize the donating ring. Okay, correct.
Yeah.
Next, if you have deactivating one, like if you have deactivating one, keep the deactivating one and reduce the normal benzene one. That's it. Okay,
Yes.
these are the oxidation reactions, beta. Clear?
Yes, sir.
Right. So as much as benzene as a syllabus part is concerned, okay, we have covered everything in this case. Clear?
Yeah.
Okay, right.